Let me see. The table is in the way. So again, this is an exam, but it is not. I ask you to defend your work, show us that you've done something significant, show us your contribution, and tell us why we should award you a PhD. I guess you will talk for about 40 minutes. Then there will be questions from all of us. Then we'll ask everybody to leave, and just the committee will stay. Go ahead.
All right, so welcome everyone. My name is Deran Schweitzer. I am defending my doctoral dissertation today, PPC operating in gamma beams, a new tool for nuclear structure. Let me turn on my mic. My major advisor was Dr. Moshe Guy, and my co-major advisor was Dr. Robin Smith, who is joining us. In this talk, I'll go through a brief introduction to the physics needed to motivate this experiment. I'll review the basics behind time projection chamber detectors, which we used two different ones in our experiments. I'll review the experiment itself that we did at the Higgs facility. I will review the data reconstruction of taking the raw results from the Higgs facility and putting it into a workable form. And then I will review the data analysis of that data and the scientific conclusions that we draw from that. So to begin, I'll start with a question from the mid-20th century, which was, how did carbon-12, or heavier elements, come to form? It doesn't seem like there's too many isotopes of mass 5 or 8, at least that are stable. In 1952, Salpeter argued that 2 alpha particles make a resonance in beryllium-8 with a lifetime of about 10 to the minus 16 seconds, and a certain density of beryllium-8 would therefore exist in stars. Hoyle, 2 years later, argued that there must be an excitation of carbon-12, which he predicted at 7.65 MeV, which is formed when the beryllium-8 and another alpha particle combine to form a carbon-12, which is excited, which rapidly decays to the ground state. This was confirmed a few years later experimentally by a group led by Dunbar. This carbon, let me turn on my laser pointer here. That carbon can subsequently capture another alpha particle and form oxygen-16. Keep that in mind, I'll bring that up again a little bit later. So the existence of the Hoyle state had been proven, but the structure of it remains poorly understood even to this day. It has been proposed that one can study the structure of the Hoyle state by examining the rotational bands built on top of it. There have been various models for carbon-12 over the years, an effective interaction Hamiltonian by Brink in 1966, nuclei clustering model by Tasaki, EFT lattice calculations in quantum chromodynamics, many others. However, it was observed that ab initio shell models don't predict the existence of the Hoyle state, and EFT calculations fail to predict the parity doublet and higher spin states in the ground state band. The algebraic cluster model, proposed by Biker and Iakello in 2000, is an interesting model because it predicts carbon-12 as a rigid triangle of 3 alpha particles. So imagine an alpha particle at each vertex of a triangle, and the rotations and vibrations of such a triangle would lead to several excitations of a carbon-12 atom. This model predicts certain states to exist, and Marine Lombari and the group that they led in 2014 confirmed that these predictions, they predicted 5- in the ground state band, existed as the D3H model, the algebraic cluster model, predicted to exist. However, several states were seen to be outstanding, and those would need to be identified to make a more conclusive resolution of this structure of the Hoyle state. So some of the identified missing states that were identified in 2013, graduate student William Zimmerman, graduated from UConn a bit before I arrived, observed a 2+ in carbon-12 at 10.03 MeV in the Hoyle band. And Martin Freer in 2011 observed a 4+, 13.3 MeV. However, several missing states were predicted the one could search for, such as the 2- in the bending band, and a 2+ in the bending band, and a 3- in the Hoyle band, which are both predicted around 12 MeV. So what is meant when I say a vibration band, a rotation band, a bending band? So the different types of motion in a three-vertex triangle with something on each end give rise to different collective bands of states corresponding to the different motions it could have. The ground state band is rotations of the triangle. The Hoyle band is often, the Hoyle state is said to be the band head of the breathing band, which is where all three particles, like they're breathing, expanded and out. So that state is a relatively large radius. And there's a more exotic bending band, which I won't attempt to mimic with my hands, that moves in the fashion shown in green here. Due to the intrinsic underlying structure of such states in those bands, understanding a band provides some information on the structure of carbon as a whole, and measuring missing states like the 2+ can provide information about the Hoyle state, which is of interest to us. And in general, it allows one to test the predictive capability or the predictive power of the D3H model, the algebraic cluster model for carbon-12. And shown here are what these bands look like and the states within those bands. So the one in blue is for this type of motion. The red one is the Hoyle breathing band, and the one in green is the vibrational band. These are predicted, and in the previous slide I had showed which ones were observed. Now, I mentioned briefly earlier that oxygen-16 could also form in stars when carbon captures another alpha particle to make O16. This capture process is often modeled with a framework known as R matrix theory. This is a phenomenological framework which relies on known information of states of, for example, O16 in this case, to model reactions and extrapolate them to other energy regimes where data may not exist. Currently, in the literature, there is a lack of data between center of mass energy of about 3 to 4 MeV. Missing states in the R matrix model are treated as a broad background with a high uncertainty, and this could be reduced with further experimental observation of high energy data, which would look for the tails of those high energy states to model that background. It was proposed by Carl Bruni in 2014 that the optical time projection chamber detector, which I'll describe briefly from our group, could allow a search for those states via the study of the time reverse photodissociation reaction using a gamma beam. So what is meant by a time reverse reaction? I'm introducing this concept here. So in stars, one observes the direct capture processes. For example, beryllium, the short-lived beryllium captures an alpha to make carbon-12, which emits a gamma, and carbon can capture an alpha and emit a gamma and become oxygen-16. In the lab, we look at the time reverse reaction. And carbon emits a gamma, absorbs a gamma and emits an alpha becoming beryllium-8, and the photodissociation of oxygen-16 hit by a gamma, producing an alpha particle in carbon-12. Why would we choose to do this time reverse process as opposed to the direct process as they occur in stars? Several reasons. One is selectivity. Using a gamma beam, one populates only the states that they want to look at, since it's a monochromatic beam of photons and can only populate certain states via quantum mechanical rules. There is low background. One only has a single well-collimated beam. There is a larger cross-section in the case of the oxygen-16 photodissociation due to the principle of detail balance, which says that in equilibrium, any kinematic process is in equilibrium with its time reverse. So they're fundamentally reversible, but due to the kinematic properties of forward and backward reaction, it turns out that the photodissociation across the energy ranges we might look at has a significantly larger cross-section, factor of 50 to 80. And lastly, in the case of carbon at least, it's a lot more experimentally viable to photodissociate the carbon that is just sitting there stable, as opposed to somehow combining 3 alphas even through the beryllium like occurs in stars. So I mentioned that we use time projection chamber detectors. Before I tell you about the specific ones that we used or studied, I'll just show you a bit about how they work in general. Here's a general schematic of how our TPC works. In a TPC, there is an active volume. So imagine a box or some container filled with a gas. An ionizing agent is sent into that volume. It could be a particle. In our case, we will use a gamma beam. It causes an ionization with the gas. Particles are emitted and ionize through the volume. Electrons from that ionization drift and are collected at an anode and amplified and records the signal. And in conjunction with time information, which is also recorded, one can do a 3D reconstruction of the track that happened. What that time element is varies. There's many different TPCs that do it in different ways. For us, it is the delayed arrival time of the electrons to that readout that provides the timing information. So the first detector that we used, our initial, the one that we developed, was known as the optical time projection chamber, which I'll just refer to as the OTPC. This was commissioned to leverage high energy gamma beams that were known to exist at the Higgs facility, which I'll also review in a little bit, for studying the astrophysical reactions which I described earlier. Notably, this is an active target TPC. It is both a detector, as it is what records information about the event, and it is also the target. It contains the gas, and the reaction itself is entirely in situ. It's within the detector itself. So just briefly about how the OTPC worked to motivate the principles. A gamma beam is sent into the OTPC. It's through this little port here on the side. There's a gas inside of the volume. In the OTPC, that gas was 80% CO2, which contains both carbon and oxygen. As you remember from a few minutes ago, both are relevant. And it also has nitrogen, which is a scintillator to produce light, which the optical time projection chamber would use for reading out images. So when the gamma beam enters, it causes a photodissociation. Those electrons drift to a multiplication grid. And in that multiplication, light is also produced by scintillation of nitrogen. That light is sent out through both PMTs for recording and also through an optoelectronic chain, which through a process I'll just briefly summarize, is eventually read out by a CCD camera, which records the track image. Note that CCD camera, it will be relevant for something I'll bring up in a few minutes. This year, the OTPC was quite a success. It led not only to the thesis of William Zimmerman in 2013, but a Nature paper that our group published in the pandemic in 2021, where we had the opportunity to examine some dormant data. And it also led to several other instrumentation papers, talks, things like that. So the OTPC was quality, but it reached its limitations. What those limitations were principally the CCD camera had a very limited acquisition rate. Even running at a reduced resolution and well-cooled, it can only record track images at a rate of several hertz. This meant that experimentalists could not use the full output of the Higgs beam. Second, the data analysis was not efficient. The manner in which line shapes and parameters were extracted from results meant that only events at specific angles could be accepted, which was just simply not efficient. And there was a scientific need or desire for a new detector to be modernized, faster readout. And that leads to the Warsaw TPC, also known as the electronic TPC, or just briefly the eTPC. This was commissioned in 2017 for use at ELINP, that's the Extreme Light Infrastructure, Nuclear Physics, in Bucharest, Romania. As this is still under construction, we used it in our experiment at the Higgs facility, which was known to work from OTPC experiments. The eTPC, in brief, has an active volume of about 35 by 20 by 20 centimeters. The internal core consists of a drift cage with amplification structures, a segmented readout anode. I'll detail those in a few minutes. So picture this box mounted on a movable cart, which allowed translation in different physical setups, beam lines, calibration, etc. And similar to the OTPC, the gamma beam is sent into a port on the side. A gas is contained inside, it photodissociates and produces some track, which is detected and the signal is later reconstructed. So some details about the drift chamber itself. First off, it's filled only with CO2 gas, as there is no longer any optical setup or readout or system. No scintillation is needed. We don't need light, simply CO2 gas produces the reaction, and you can detect with that. The drifting electrons, so shown here is a gamma beam sent in, photodissociating an oxygen-16 into a carbon and an alpha particle. Those drift and are collected and multiplied by 3 gas electron multiplier, a GEM, foils from CERN. These are thin, perforated, copper-coated Kaplan foils, which produce a high electric field in a narrow, these little narrow holes, which are about 50 microns wide. And the charge is read out by a novel PCB, printed circuit board, consisting of a redundant array of three strips, U, V, and W, which are oriented at 60 degrees to each other. That deserves some special mention, as this was a considerable advancement. These UVW strips produce independent readouts of the charge position and produce virtual pixels, sometimes called voxels, that facilitate reconstruction for a given time slice. So the information from the detection of the strips is synced up with vertical track info from the drift velocity, which is known because we constrain a certain electric field in the volume. And since we know the other properties of the gas, we know the drift velocity and therefore how long it will take electrons to arrive, which allows a 3D reconstruction of the track and also with simple event topologies for later analysis. This is read out by 4 oscillate boards. That's these 4 boards mounted to the top of the detector and sent to a data acquisition system for further processing and analysis later. In general, this facilitates extraction of polar angles, azimuthal angles, and just allows easy identification of multi-particle reactions within the detector. So a brief mention of a project I did when I first joined the group. I assisted with some Maxwell simulations of the drift field inside of the ATPC. So as I mentioned, an electric field with well-determined homogeneity is required inside the active volume in order to maintain a consistent drift velocity and allow known reproduction of tracks later. So we perform simulations using a software called Maxwell, produced by ANSYS, to simulate what the electric field would be inside the detector for various configurations of the drift cage. So for example, we might vary the number of electrodes, the spacing between them, the pitch, etc. Due to time constraints, and since this was just sort of my first project joining the group, we just looked at 14 configurations and saw which one was the most suitable, and this informed the design of a miniature version of the TPC that was used for studying the actual TPC that was constructed a few years later. And of course, the goal was the configuration with the best electric field stability. And what I show here is just a sort of a 2-dimensional slice of that drift cage. Because it's a symmetric volume, we ran the simulations on just a 2-dimensional slice, and by symmetry it would apply to the 3-dimensional cage. And so just, we looked at a lot of them, but what I show here is the most optimal configuration of the electric field that we determined. The green, the solid green, represents the nominal 380 volts per centimeter electric field that was determined to be the desirable for the setup as designed by the University of Warsaw. Each gradient line, showing you the edges here, I'm showing you my pointer, is 1/7 of 1%. There's not many of them. So within this volume, we indeed have a well-determined electric field. And just to point out, the red and blue regions, they're not in the actual active volume, so they're just off scale, so don't worry about that. And just for fun, here's a picture of me and Sarah at Warsaw in June 2019, pre-pandemic, helping to install a printed circuit board inside the ATPC itself. And our collaborator, Dr. Nikolai Shok, who is principal designer, is helping us in a Warsaw clean room to install components. So now let me talk about the facility that we use to produce the gamma beams that we use in our experiment. So our experiments took place at the High Intensity Gamma Ray Source Facility, HIGS for short, which is at Duke University. The general operation is as follows. A LINAC produces electrons that are accelerated to a very high energy, about 1.2 giga-electron volts, and they're injected into a storage ring. That's the ring here. These electrons pass through something called a wiggler. It's an optical klystron, a series of them, which undulates, wiggles the electrons, which produce synchrotron radiation. That's an initial beam of photons. Mirrors in an optical cavity at the bottom of the ring are designed so that returning photons strike a second electron bunch halfway around from the first at the halfway point. And the Compton scattering of the FEL beam, the free electron laser beam, and the electron bunch produces a gamma beam, which is output collimated and sent to a target. In this example here, this shows the OTPC operating in the Higgs facility. This is taken from our Nature paper, which overviewed the OTPC's use in Higgs. So for our experiment, we looked at two measurement series in April and August of 2022. We took our detector, which was constructed in Warsaw, post-pandemic, shipped it to Higgs, reassembled it at the Higgs facility, and then we installed it in the upper target room at Higgs. Shown here on the left is the ETPC as it was placed in the upper target room. On the left, it's a bit off screen, but shielded by lead bricks, is the gamma beam, the source of it, the pipe. It is sent in through this the window on the detector, and the reactions occur inside. And the offset boards read out the data and send it to data acquisition for later collection and analysis. And the rest of this is just instrumentation modules. So the energy range we looked at in our experiment was about 8.51 to 13.9 MeV. The focus of my thesis was the 10 MeV and above results, as I was looking at high energy results for carbon and oxygen photodissociation. So during the campaigns, unprecedented data and a significant amount of it was acquired, over 4 terabytes. Parsing that proved to be quite a considerable task. So we elected to do a threefold process to tackle this onerous task. First step was a pre-analysis, mainly done by our collaborators at the University of Warsaw and Sheffield Hallam University. This predominantly took the raw output of the offset boards, which was some binary signal information, and transformed it into a workable, tractable representation of our tracks that we could work with. And then we developed, Sarah and I, and with help from the collaborators, a primary analysis framework and a secondary analysis framework. The primary analysis framework looked at a track-by-track individual analysis of events that were pulled in the entire data set. And the secondary analysis framework looked at, of the aggregate data set, we go energy by energy, and we will seek to isolate the oxygen-16 photodissociations and the carbon photodissociations for further analysis. So just to kind of guide the eye and show you how these events actually look in the detector, here's an example of an oxygen photodissociation event. So that's to remind you, oxygen struck by a gamma ray, photodissociating to an alpha and a carbon-12. This is taken at 11.9 MeV. We call this a two-prong event, so-called because from an interaction vertex, which is just ahead of this little yellow end here, the carbon is the more intense short end of the track, and the emitted alpha particle is the longer end of the track. And that's well represented from the information from the U, V, and W strips in this case. Here is what we would call a three-prong event, that is a photodissociation of carbon-12 to beryllium-8, which rapidly decays into two lower energy alphas. Excuse me. In the U and the V strip, you don't really see much information. This can happen depending on the orientation of the event. But in the W strip, you can see it kind of looks like an archer's arrow. That is the photodissociation. The long end is the principal alpha from the carbon-12, and the beryllium-8 is decaying into the two shorter range alphas that are at the right here. So the first step of the primary analysis framework was to filter out the background. So we filtered low charge events from a prior initial crude look at the data set. We had a sense of what charge would correspond to a reasonable event on the detector. And so we could place a filter such that only events that we could screen out depositions that certainly did not correspond to an actual physical decay. And then we applied a succession of 3 masks. So the first mask, applying it to the event you just saw, I'm showing you the W from this, was a removal of the background. So we fit a Gaussian to a 1D histogram of the pixel intensity, and we only preserve pixels that are at the mean plus 3 sigma from that background. The effect of that was to screen out all of the low-level background from the event. That's why all that blue is gone here. The second mask was a nearest neighbor. What this means is we only kept pixels that were adjacent to 5 or more neighboring pixels. Therefore, if there were just random little islands of things that happen to be slightly intense, they would be filtered out. And this would preserve the track and maybe a couple other small islands. And the third mask was to preserve only the longest track of the remaining data sets. So here, that would be, in pretty much every case, it should be the track itself. Here in the W strip, it's not necessarily clear that this is discontinuous from the rest of this tail, but in the U and V, there would be some information that showed this, and so the longest track could be isolated from those. Next, we identify parameters defining the track, and we want to convert those to Cartesian XY coordinates. We first look at the extreme pixels, that is the pink and the purple, the endpoints of the track, and we look at the most intense pixel between them, that is the brightest pixel. With this, we find the interaction point. So we look at the dimmest pixel between the bright and the extreme pixels after projecting. We identify it as the interaction point because particles shed more energy as they lose energy. So the minimum intensity pixel is going to be where they have the most energy, which is the point where they began to exist, the interaction point where the photon dissociation occurred. And I show it here. Unfortunately, it was in green as the way it was out in the software, so I drew an arrow. But this minimum pixel right ahead of the long end of the ion, before the alpha, is where the photon dissociation was identified to occur. So stage 2 was now we can go to the secondary analysis framework. So the PAF, I should mention, ran on the entire data set and took a very long time to run. So just to give you an idea, we had to take multiple laptops from our lab that had been repurposed from something else, network them in our house, in our basement at the campus, and set up kind of a mini HPC of our own making, where we kind of parallelized all of the different energies and runs from all of the entire data set, and it took hundreds of hours. Meanwhile, the SAF was much quicker, running within a day or maybe a few hours or less. An aggregate analysis of that filter data set, and the goal of this was to isolate events of interest and extract relevant physical parameters that would allow classification of the reactions. So the first filter from the secondary analysis framework was a filter based on track length. So using external programs and tools, for example, SRIM, which is the stopping range of ions and matter, we could look at potential lengths for tracks for given experimental conditions. So for example, at a given gas pressure, at a given energy of the beam, we know that an emitted alpha should have a length of a certain size, and we could filter tracks that did not broadly satisfy that length or deposited an anomalous amount of total charge. And so we plot here the total length of the track versus integrated pixel count, which is analogous to the charge deposited. And in this main intense region, we identify that as carbon-12 and oxygen-16 events, because that's what the track lengths would be. And the longer length tracks would correspond to unwanted, in this case, oxygen-17 and 18 photon dissociations, which would be longer in length. The second filter was a volumetric one. We filter on what is known as the fiducial volume of the detector, that is the active area of the detector itself. We know the parameters of the detector from the specifications from the design, so we can place a cut or a filter and screen all events that are outside a given volume or near the edge of the detector with a 1 centimeter safety margin, just to make sure that something wasn't like too borderline and just accepted. And all those were filtered out. The next one was a filter on the interaction point. We wanted to make sure in this filter that all event interaction points were generated by the gamma beam itself. So we're using this gamma beam to cause photon dissociations, therefore events of interest should be beam-induced photon dissociation events. We filter events that are far from the beam line in the y direction or near the edges of the detector itself. So how we did this was we first took a y projection of this track, so this narrow region here. Along the whole y-axis, we project and fit a Gaussian to it. As you can see, it's very narrow because the beam is narrow width relative to the size of the detector. And we exclude all events that fall outside of 3 standard deviations from that beam. And along the x direction, which is pretty much the whole length of the detector volume, we exclude events that are near the edges. So we find where an alpha, if it occurred at this x coordinate, could potentially be long enough to escape. And we say, okay, we're going to filter all alpha particles at that region and at that minimum and beyond. And that's these red thresholds here. So anything here could possibly produce an alpha particle long enough to escape the detection, and an event that is not fully contained is not able to be reconstructed correctly. So Those are all filtered. And that resulted in this total filtering here. It's kind of an overlay. There's overlap between these two, but only the central narrow region of well-defined beam-induced photodissociations was now complete. At this point, we wanted to now we now had data sets for oxygen-16 and carbon-12 isolated for each. So we wanted to convert to the center of mass energy frame in order to properly calculate and compare with known values. So we convert to the lab frame to the center mass frame to account also for the fact that the target is given some small amount of momentum from the incident gamma ray hitting it. We calibrate this energy using resonances in oxygen-16, which are known from the literature, and we can convert from detector coordinates to beam coordinates, which facilitates comparisons with world data because beam coordinates are essentially the system that everybody would use to describe events with standard coordinate systems for measurements. And here is how that selection would look. So using Root, which is an analytical software framework from CERN, we could select data sets corresponding to each type of photodissociation. So this island, this kind of blob here, would correspond to oxygen-16 photodissociation events. So using a tool called T-cut, which lets you literally trace a selection, we could cut around only that and rather conservatively avoid all of the carbon and make sure we don't have any contaminating carbon in our selected data set. And after selection, all of the other events are removed. And on the right, this is the surviving data sets of oxygen-16 photodissociations that were analyzed in our analysis. I will also point out that the calibrated center mass energy uses the kinematics of oxygen-16 for this calibrated center mass energy because the kinematics of the breakup of carbon and oxygen are different because there's different ions involved. And for carbon, it's essentially the same process. Use the T-cut tool in Root to make a selection around the dissociations of interest, carefully avoiding the other region. You can see here there's statistically much less carbon, as expected at these energies due to resonances in oxygen. And in this case, of course, we calibrate and using the kinematics of carbon-12 for the dissociation. At this point, we made one final cut. We noticed that events with extreme azimuthal angles, so close to between 0 and 30 degrees and 150 to 180, were not reconstructed well by our algorithm. These are events that are flat with respect to the readout geometry, so there's not a big distinction in time, and it did not do a good job reconstructing those low phi or extremely high phi events. And so we keep only events with a phi between 30 and 150 degrees. That should say not flat with respect to readout. So those events were preserved, and we cut all the ones that were at the extreme angular ranges. And that was the conclusion of the secondary analysis framework. So concluded the filtering of events. At this point, we now had separated reaction data for oxygen, photodissociation, and carbon. For each event in the data set, event by event, we had center mass energy of the reaction, the polar and azimuthal angles of the event, the photodissociation, and the length of the track in Cartesian coordinate space. As just a sort of an example, for the 11.9 degree data sets, in the initial sample, so detected from recorded at Higgs in our GRAW files, there were 168,000 events. This, of course, included noise, competing reactions, sparks, things that should be filtered and were. And surviving after all of the cuts that I described, about 26,000, or about 15.7%, were oxygen, and just 815, or about 0.5%, were identified as carbon photodissociations. So, with that data well filtered, we could progress and proceed to the analysis. So, I'll remind you of the objectives that I outlined in the beginning. Objective 1 was the exploration of high-energy oxygen-16 photodissociation data. The tails of high-lying states in oxygen-16 were sought to reduce the background, the uncertainty in the background for R matrix theory modeling and extrapolation to desirable astrophysical energies. And for carbon-12, also looking at the high-energy data, we would look for high-lying states in carbon-12 as predicted by the algebraic cluster model, and also extend the prior results of Zimmermann using the OTPC and where they overlap compared to assess how the ETPC performed. And in an overall sense, the main objective was to demonstrate the viability of the ETPC as a tool for nuclear structure and astrophysical studies. I will point out that the nominal beam energies that I examined in my analysis were 11.1, 11.5, 11.9, and 12.3 MeV. The higher energy data was not able to be analyzed because the parameters chosen for the experiment, like the gas pressure, did not allow for sufficiently contained tracks, and the higher energy data didn't have very well good statistics anyway. So just these four entities are analyzed here. So we begin by discussing the oxygen-16 photodissociation. We'll look at the cross-section of the reaction. So measurement of cross-sections, reaction cross-section, is a useful bellwether for the capability of the TPC to perform accurate measurements over a wide range of energies. So in order to do this, we needed the yield, which is the binned center of mass energy data, which we had, a profile of the gamma beam used in the experiment. These were obtained from fit to skew Gaussians using a simulated gamma beam produced by Tunnel and fit by our collaborators at the University of Warsaw. These are smeared by the detector resolution because that will, of course, affect how these are resolved in the detector. And the theory in this case was an R matrix fits to the direct capture global data as produced by De Boer in 2017. And the approach was to scale the cross sections with the convolved normalized gamma beam to the R matrix theory produced by De Boer and assess if the ETPC could reliably measure and be in agreement with those global results. So as an initial check, we looked and we plotted and saw if De Boer results were viable fits to the global data. And they are. So De Boer's fit closely matches the direct capture cross-section data, which is taken directly from paper by Sherman and Brochard. I should point out that there is poor fit information between 4.5 to 5 MeV. There's just no data in that region, and therefore limited conclusions can be drawn in that range. And further, secondly, there is an average difference of 18.5% disagreement between De Boer and the global data. And this places a fundamental limit on our scaling factors. So after that assessment, we take our binned center of mass energy data and we divide it by the convolved normalized gamma beam profile, producing relative cross sections. Again, we did not have an independent measurement of the beam intensity. There was an HPGE detector that recorded this, but there were no unfolding matrices available at the higher energies, and so we had to rely on the simulation to get the beam profile, beam intensity. We could scale up these relative cross-sections to the known oxygen-16 cross-sections from De Boer. This provided an absolute assessment of the beam intensity, and this was done by doing a chi-squared minimization of the scale factor, energy by energy, to the De Boer data. So we did this for all energies, because the beam intensity varies at each energy provided by Higgs. And anywhere that there was overlap, so for example, at the tail of the high tail of the 11.5 MeV data, there might be some overlap at the bottom tail of 11.9, since it's a broad beam. We would take the average where those data overlapped. Just to walk you through a brief example to guide that understanding. On the left here is the yield. This is the histogram results of the ECM data from the 016 data set at 11.9 MeV. And on the right is the Gaussian beam produced from the simulations I described, normalized to have an area of 1, and convolved with the detector resolution of 72 keV. We scale the yield up to De Boer's R matrix fit in the relevant region, which is defined by the central 1 sigma of the beam profile. De Boer is convolved with the detector resolution and scaled by detail balance, as he did direct capture data, and that is needed to compare to photodissociation, here, kind of reverse. We then chi-squared minimize the difference between them and repeat this for a beam shift of plus 30 and minus 30 keV, which was assessed as the uncertainty in the provided beam spot from Higgs. This yields a cross-section of each energy, and we take an average. These value ranges for the scaled cross-section and the scale factor itself define systematic uncertainties in the experiment. So here it is. So de Boer was rescaled to the photo-dissociation reaction via detailed balance, and we compare them to the ETPC results, scaled up to de Boer, and shifted to the center of mass frame. That means we subtract the Q value for the reaction to shift from the beam energies, which were 11 to 12 MeV, down to the center of mass frame. The color bands, so the blue is the direct de Boer fit. The color bands are the plus and the minus, the green and the red. They represent the 18.5% uncertainty estimates, which came from the average disagreement of de Boer and the global data. And we see that the ETPC results agree well with de Boer with an uncertainty. Due to the lack of an independent beam intensity, we cannot make a definitive statement regarding the background from these results. We may be scaling to a background that is present in de Boer's fit, and we wouldn't know. However, we can conclude the ETPC viably may measure cross sections over multiple orders of magnitude for this reaction. We may also look at the angular distributions of the O16 data set. So the properties of each of the angular distributions at each energy could indicate the presence of a background. So we wanted to look at angular distribution parameters for interfering states. It was known that there's two resonances roughly in the energy range that we're looking at. And so we used a fit method, an unbinned maximum log likelihood routine, and fit using a parameterization coming from Dyer and Barnes in 1974. They published a partial wave decomposition for interfering 2+ dipole and 2+ quadrupole, 1- dipole excitations. And here is that partial wave decomposition. The A1 is the amplitude of the E1 dipole excitation. A2 is the quadrupole excitation amplitude. And phi12 is the mixing phase or the interference angle between those amplitudes. And that is what we fit to. And here are the angular distributions. What we conclude from these and the data, they're extracted parameters. At 11.1 and 11.5 MeV, there is a strong evidence of an E2 transition. This is observed from the E2 over E1 ratio being significantly above 1. It's about 9.1 and 6.98. At 12.3 MeV, it's strong evidence of a pure E1 transition. The E2 over E1 ratio is about 1/7, significantly below 1. At 11.9 MeV, there's just some incoherent sum of E1 and E2 amplitudes, where phi12 is about 90 degrees, and cosine of phi is 90 is 0. The fit does not require any background term. The data is explicable without a background amplitude. Granted, of course, that de Boer may be including one in the scaling that we did to his data. And now we can turn to carbon. So for carbon, the methodology is quite similar to the oxygen analysis. From the carbon data set, we have the angle in the center of mass frame. Since we're interested in granular changes over the energy range, and there's to look at that, we subdivided the 4 carbon energy data sets, so 11.1, 5, 9, and 12.3 MeV, into smaller slices to look at how the parameters would vary over an energy range that was more refined. And then we fit again with the Dyer and Barnes partial wave decomposition, which again is suitable for this reaction to interfering amplitudes. And what I show here are a comparison of the ETPC measurements, those are in blue, and the OTPC measurements, which are in red. The constant value of the extracted phase, the phi12, between 11.1 and 12.3 MeV suggests the lack of a new state. We don't see any resonance or spike. And given that the Coulomb phase shift of arctan of 8/2 is about 25 degrees over this range, we can conclude 2 equal magnitude amplitudes exist that are separated by 35 degrees. The measurements of the E2 over E1 ratio confirm this. The ratio is approximately 1 over the energy range that we are looking at here. I should point out that the 12.3, the most extreme data set, I'll show it here, does not have very good statistics. It is potentially the case that there is some oxygen contamination in that data set due to the far greater likelihood that the decay at that energy will be oxygen. So we should take caution in gleaning anything very useful from the 12.3 MeV data set. However, the results show the influence of the known 2 plus and the 1 minus amplitudes at 10.03 and 10.9 MeV. And the remaining amplitudes simply just show a flat E2 over E1 and a relatively flat phi over 2, as I showed in the previous slide. And in conclusion, we deduced that there was a lack of a new stage between 11.1 and 12.3 MeV from the angular distribution analysis. We may also look at the cross-section of carbon, as we did for oxygen. Fortunately, because we already had a scaling factor from the oxygen 16, which provided an assessment of the absolute beam intensity, we could compare to theory and also, in this case, to experiment, the results of Zimmermann. So we compare experimentally the ETPC 2025 to Zimmermann's thesis in 2013, and the theoretical comparison in this case is a single level R matrix fit by Hans Finbo, which is a Bright-Wigner parameterization of R matrix theory, and he fit to the 2 plus. So the ETPC's results are seen to agree with Zimmermann's up to about 11 MeV, where Zimmermann's data ends, and the ETPC extends these to higher energy. We observe that the ETPC results lie on the tail of the 2 plus, as predicted by Hans Finbo in this fit, and the results indicate a flat, near uniform total cross section in the energy range of 11 to 12.3 MeV. So the cross section is well fitted by the Bright-Wigner. And we conclude that there is, from this as well, no strong evidence for a new state in carbon-12 over this energy range. There's no resonance, there's no spike, there's nothing to indicate the presence of a new state. Just a brief summary. For oxygen 16 photodissociation, the cross sections broadly match the Bohr fit over the energy range. The angular distributions reflect this consistency. The ETPC measures over multiple orders of magnitude, but due to the lack of an independent beam profile, no conclusive statements can be made about the presence or absence of a background term. For carbon-12 photodissociation, we agree with the results of Zimmermann published in 2013, extend them to higher energies, at which we see no evidence of a new state between 11 to 12.3 MeV approximately, and the angular distribution reflects this. There's no spike or significant evidence for a new state between 11 and 12.3 MeV data sets as we reported. Thank you.
Thank you, Deran. No clapping. This is not. This is an exam. Thank you. A bit on the long side, but that's all right.
47 minutes.
Okay. So, following the tradition in our department, we open the again exam, but not really an exam, to questions from the public. Also, people on the internet. That where are they?
The internet's here.
Okay, so Sarah, you will see if anybody on the internet want to ask a question. So first, from people in the audience, the committee will ask question and in closed session. Okay, I see no question. Okay.
On that last slide, I guess, when you have the
Carbon cross section.
Just a moment, let me jump right there. So the last slide before the references or the last image?
The carbon cross section.
Yeah.
that one. So why do the points have a second hump, but the line doesn't?
So Hans Finbo only was fitting to the 2 plus, which was the result of Zimmermann in that paper.
Okay.
So he didn't include the 1 minus. But the 1 minus does not have a long tail, the 2 plus does, so
Okay.
it is predicted to, the data should follow it.
Okay, if there are no further questions from the internet, Sarah?
They don't.
No.
No one has a question.
No, nobody.
No one has a question.
Okay, so may we ask you all to leave? Have a stroll in the campus. Don't go too far. And the committee will